attention to it. That A point shouldn't be x. Okay, so we don't consider this point first. Okay, so once we find the candidate of limit point, we open a random open ball here, and to see that whether that open ball has the intersections with the intersection of that open ball and the set A is non-empty, which means we can find a small a one here that is contained within this open ball, epsilon 1. And notice that the definition is for all epsilon larger than 0. That means no matter how small the ball is, even you open a small open ball, look like this one, you can still find a point within A, and it's not equals to the reverse point you pick. Okay, so if that is the case, then this reference point x is the limit point of the set A here. Okay. And what if you pick up the reference point this way? Let's call it x plane. Of course, when you have an open ball that is large enough, you can certainly find some point within A that is going to be contained within that open ball, right? But once you shrink that open ball, for example, look like this one, then you fail. So that point x plane is not an open ball of set A. Okay, so that is the idea. Okay. Then is the question 7. Yep. So these 3 following statements are equivalent in when we are in a metric space here. So A is closed for any sequence exons in for any sequence is contained in A. When it converges to X, then the X must be in A as well. Okay, and the A contains all limit points. Okay, so these 3 statements are equivalent, and I'm going to prove it very quick. Okay, so we start from proving that the first statement implies the second statement. So what we have is that A is a closed set, right? That means AC, the complement set of A is opened. So suppose that the sequence converges to X that falls within the complement set of AC here. And because it is open, that means we can find epsilon larger than 0 and open a ball that contain that ball is contained in AC here. Okay, and we can find a natural number big N here, such that for small n, when the small n pass the big N here, the sequence will be arbitrarily getting closer to the convergent point. However, this means that for all elements, when the small n larger than big N, it also fails in the complement set. And that is contradicted to the statement here, because the sequence has to be in the set here. But we found some elements that actually fails outside that A. Okay, so there's a contradiction there. I think they turn off the AC or something. Okay, let me be quick. So then we're going to prove the second statement implied the third statement. So what does that say? Okay, right. We start from this way. So for all the limit point of A, we can construct a sequence that totally fails within the set A, like the way I did it right now here. Okay, so we pick up the limit point X and we shrink the circle, and then we can always find a point that within A, and also the sequence is going to getting closer to X as well. And because of that, and because of the second statement, it implies the convergent point X fails in A. Okay, so that we complete this proof. And then the last one, the third statement implies the first statement. Okay, so given 3 for all X in yeah, because that is A contains all the limit point of A, right? So if the point fails outside A, which is the complement set of A, that means you can find an epsilon larger than 0. For example, like in this case, the epsilon falls outside the set A, and then you can find an epsilon that could open a ball that have a has an emptied intersection with the original set A here. Okay, and what does that mean? That is actually the definitions of open, which means